to thank the organizer to invite me here for the first time in Chile and to have the opportunity to participate to this workshop that is very interesting and ambitious. I am a mathematician that has not a good sensitivity of biology and maybe physics problem. So I'm sorry, but my talk, it will seems to be abstract and theoretical, but maybe someone could find a way to apply my results. Surely, this talk was born by a practical problem that is what is the decoherence. That Blanchard introduced in the first talk of this workshop. The term of decoherence was used in literature in a very different meaning, but always when we wanted to underline that is an emergency of a classical feature in the evolution of the open quantum system. It is quite difficult to find out a clear and well-recognized definition of decoherence, and with Raffaella Carbone and Veronica Umanità, started from the definition of Blanchard in 2003. This is not the only definition, as I will show in the following slide. And but in our work, we wanted to understand better this definition, to understand what are the implications of this definition for other properties of the semigroup, of the evolution of the open quantum system, to study the comparison with other definitions, and after several years, I think that we have a more clear picture of this puzzle for us. Now, before starting by recalling the definition of Blanchard, I want to fix what are the objects of our studies. We work with an open quantum system that is described by von Neumann algebra M, acting on a complex Hilbert space H. We consider only Markovian evolution described by a quantum Markov semigroup that is a family of linear bounded operators on M that are quick star continuous, Markovian, and completely positive. We know that the completely positive and the Markovianity of this semigroup implies that we are working with contraction, and this property is a good tool for our proof. In general, for our proof and result, often we can work only with the positivity of the semigroup and with the Cadison-Schwarz inequalities. But now in this talk, I work with this hypothesis. Now, I think that if I understand better the problem, that the most popular idea of decoherence is that the reduced density matrix becomes diagonal with respect to some basis selected by interaction. And in many applications, we want to minimize the impact of decoherence by select some sectors in the space of states that undergo unitary evolution, such that they are preserved by dissipation. And this is, I think, the idea on which the definition of Blanchard-Dulkiewicz is based on. In fact, we want that the system can be decomposed in two parts, roughly speaking, in one component in which we have a unitary evolution, and another one in which the evolution of the system vanishes in time. To be more formal, we want that M is decomposed in the direct sum of M1 and M2, where M1 is a star TT invariant von Neumann just subalgebra of Mn, and such that M1 is the maximal von Neumann subalgebra of Mn on which every operator TT acts as a star automorphism. The second one, M2, that we want not trivial, is a TNT invariant, star invariant, and weak star closed subspace of M, such that every element of M2, the evolution of element of 2 goes to 0 in the weak star topology. Now, by the definition, it is clear why we call M1 the algebra, the decoherence-free algebra, or also the effective, the algebra of effective observable, and M2 the space of a non-detectable observable. Because, roughly speaking again, when we watch the evolution of X under TT, after in a large time, we can see only the action of the evolution of X1, that is the part of X in M1, and M2 disappear in such a sense. Now, this is not the only definition. We have other definition. One of them is based on another intuitive idea of the coherence, that is that we have the coherence when the coherence loses in time. What are the coherence? We work with a orthogonal normal basis of H, a density matrix rho, and we want to analyze the evolution of these states, so we must work with the predual semigroup. We have this natural pairing, that is the coherence. And we said, better, Rolando said, that there is a measurement decoherence that I indicated with MD under the state rho if exists a orthonormal basis such that this coherence goes to 0 for T large. For example, when if rho is an invariant state for the semigroup, this is equivalent to say that rho is diagonal with respect to this basis. It is obvious to see that this definition can be valid for a state rho, but not for another. So we can want to have a strong definition of the coherence that I indicated with SMD, in which we required that MD holds for every initial state and privileged basis S, En. Now, 2 years ago, we discussed a lot with Rolando about this definition and definition of Blanchard, and we find some relationship between them, but in general, these definitions are different, and I will try to show it at the end of my talk. Now, during most of my talk, I work with a definition of Blanchard and Kelvich. No. Now, the definition of Blanchard, in the definition of Blanchard, there are 2 spaces that appears, M1 and M2, but in general, we don't know if this space exists. In fact, even M2 that appear more easy than M1 to find has a problem, a hidden problem, because we know that every element of M2 must satisfy the condition that the weak star limit of its evolution goes to 0, but in general, it is not the vice versa. So the first step of our analysis was to find two candidates to be correlated or to be exactly M1 and M2. And these two candidates, one are NT, that is the same space introduced today by Professor Raggio, but with another name, notation. And NT is defined in this identity, is the biggest von Neumann subalgebra of N, on which every element of the semigroup acts as a star homomorphism. So in general, M1, when it exists, it's contained in NT, but NT is in general bigger than M1. We have some condition in which, some situation in which we have the identity. For example, when we work with a uniformly continuous semigroup, or when there exists a faithful normal invariant state, or when NT is contained in the set of the fixed point. But in general, we don't know if when we have the identity. The other candidate for M2 is M0, that is defined in a natural way. It is the set of all observable such that this weak star limit goes to 0. M0 is a norm-closed star invariant space of M, which is TT invariant, but in general, it is not a weak star closed. That are the conditions that we want for M2. So our problem was when M1 is equal to NT, and when M2 is equal to M0, and when the decomposition is given by NT and M0, or when there are other decomposition. As I have just said, there are some particular cases in which everything works in the wonderful way. For example, when if we have that environment induces the coherence, and when we work with a uniform continuous semigroup of B of H, and when there exists a faithful normal invariant states, then M1 is equal to NT, M2 is equal with M0, and we have a unique decomposition if and only if NT, the intersection of NT and M0 is equal to 0. It's trivial. Now, when we started our work, we started with a simple case in which everything works. That is the case of finite dimensional setting, when we can consider M the set of a matrix of a dimension n. In this case, we have that always, and the intersection of NT and M0 is trivial. We have so that the coherence holds if and only if the decomposition is given by NT and M0. And in this case, we have also that the decoherence is equivalent to the existence of a conditional expectation from M to NT. And this is not a surprise, because in the definition of Blanchard, in his paper, in the definition appears the notion of conditional expectation in the same definition. In the particular case in which there exists a faithful invariant states rho, then we have that always the coherence holds, and M0 is the orthogonal complementary of NT with respect to the scalar product induced by the states, and the conditional expectation is the orthogonal projection onto NT. As Guido Raggio said in this morning, in this case, we have also a good criterion to understand when we have the coherence, because we work directly with the spectrum of the infinitesimal generator, and we have that if the eigenspace corresponding to the eigenvalues with real part equal to 0, related to the infinitesimal generator are contained into NT, then we have the coherence, and these conditions are equivalent. But the proof are based on the Jordan decomposition, or on the fact that every norm are equivalent because we are working with a finite dimensional space. And so those proofs can be can be brought, okay, in the infinite dimensional case. And in fact, when we work in this case, we have some problem. In particular, we don't know if the intersection of these two spaces is trivial. And in particular, in this case, we don't know who is M2. Then, even the existence of a conditional expectation, it is not clear. It is equivalent with the fact that the environment induces the coherence. Even when we introduce the another assumption of this conditional expectation, that is the normality. In fact, we have that, for example, if we assume that the coherence holds, then we can always define this projection E in this way. It is quite natural. But in general, we cannot prove that E is a contraction. So in general, we don't know if it is if we have the coherence, and we cannot say that E exists a normal conditional expectation. At the contrary, we have that if we start with the existence of a normal conditional expectation E from N to NT, we can decompose M in this way. But this, in general, this is not the decomposition that we want, because in general, the kernel of E is not TT invariant. And so it can not be the space M2. Now, in the following slide, I will show an example in which NT, the intersection of NT and M0 is different from 0. And it's the following. We work with the von Neumann algebra of bounded and linear operator E of H, with H is L2. L is the projection onto the space of the odd function, and the Hamiltonian is the Laplacian, or minus Laplacian. Then this is the infinitesimal generator expressed in the Liebland form. And we have that in this case. We have that environment induced the coherence. We have an explicit formula for M1 that is equal to NT. M2 is described by, in terms of L and L orthogonal, that are obviously the projection onto the space of the event function. And in this case, NT is the image of a normal condition expectation, but we found an element on NT that belongs also in M0. This is a pathological example, and by this example, we hoped to find some environment in which the result was better. And in particular, in this example, we miss the existence of faithful normal invariant states. So we thought that the existence of faithful normal invariant state was the key to obtain very beautiful results. And we added it. In this case, unfortunately, we have not marvelous result, but something similar to that. We have that if we assume that NT is the image of a normal condition expectation, we have that these 5 conditions are equivalent. And if one of these, the previous condition, is verified, then we can say that the environment induced the coherence, and M2 is the space. These 5 conditions, for example, the third one is easy to check because we call it that E is compatible with the faithful normal invariant states omega. So now we have a good candidate for M2, that is the space, and but it remains the problem then if the composition is unique. But what we find is that if we assume that the coherence holds and M2 is this space, then NT is the image of normal condition expectation. So there is this equivalence. The presence of a normal condition expectation is important, fundamental in this setting. Now, the addition of the assumption of the existence of faithful normal invariant states allows us to have some help for our proof. In particular, we have that it is quite natural to consider the scalar product induced by these faithful normal invariant states, omega, but we must observe that in general, the von Neumann algebra M can be not closed with respect to this scalar product. So, and as a consequence, also NT can be M is not complete, and NT can be not closed with respect to this norm. And so we cannot define E as the orthogonal projector or NT in general. But the natural next step is consider the completion M hat of M and the extension of the semigroup of M hat that is T hat. Now this new semigroup is a strongly continuous semigroup of a contraction of M hat, and now we have in general M hat. There is a natural embedding. Then we can have a conditional expectation E from M to N T. Then we can consider the closure of NT with respect to the norm induced by omega. Here we can consider the natural projection because here we're working with in a Hilbert space. Here the natural embedding, but unfortunately without additional assumption, this diagram doesn't commute. And in particular, we have a good result only when we consider that not only E is a normal conditional expectation onto NT, but when E is compatible with omega. In this case, the diagram commutes, and we have also that this decomposition of M hat given by the closure of NT and its natural orthogonal complementary is an isometric sweeping decomposition. The terms of isometric sweeping decomposition was used in the paper of Kiewicz, and it seems to be an appropriate way to describe the composition of the system in two parts. One in which the evolution is unitary for a suitable norm, and the second one that vanishes to zero in the sense that is according with the setting in which are approaching. And in our case, we have that T hat acts in a unitary way on the closure of NT, and the weak limit of this semigroup goes to 0 for the remnant part. And so we have that there is the existence of decoherence for M induce a decomposition, a good decomposition of the space Hammett. And in some sense, we can come back because we have that the two space, one. If we intersect this space with M, we obtain NT and M2. So we can move from this part. We have also found another relationship within another decomposition, that is the canonical decomposition. That is the case in which we can always consider for a semigroup T hat the space K defined in this way. And we can decompose M hat in two parts, K and K orthogonal. This is called canonical decomposition of T hat, and K is the maximal closed subset of M hat on which T hat acts in a unitary way, while the restriction of T hat to the complementary K orthogonal is completely non-unitary. And we have, in general, K, unfortunately, is not the closure of our NT, because in general we have only an inclusion. But if we assume that every element of the semigroup TT commutes with the modular group associated with the state omega, then we have the K is equal to and the closure of NT. So in this case, we have that these different decomposition at priori are equivalent. And here is how to pass from AD to a canonical decomposition. Now, I come back to the comparison between the definition of environment induced decoherence and measurement decoherence. I don't want to explain in detail this result because they are very preliminary results. But in this case, I want only to underline that if we have some not trivial hypotheses, we have that in some case, ID implies MD, and for the second result, we have that MD implies ID. But the conditions are strong. For example, we want to work with a particular privileged basis and a related diagonal part of the Neumann algebra. We want that the semigroup preserve this diagonal part and also the off-diagonal part. And for example, that NT is contained on D. In this case, in some sense, the definitions are equivalent, but in general, they are different. Now, in the last part of my talk, I wanted to show a particular case of semigroup that for us is a box to take example. That is the family of generical quantum Markov semigroup. For us, it was a useful box because, as I will try to show, it is easy to understand when there is decoherence, when there is MD, and so because the criterion are based on a classification of a classical Markov process. So everything becomes more easy. Now, I recall briefly what is a quantum generical Markov semigroup. We work with H, that is the space of L-square sequences. M is equal over B of H. En is the canonical orthogonal normal base of H. We have that the generator of this semigroup is given by this Lindblad form, and it is not equal to the definition given by Franco, but it's very similar. It's the same. We have, and we have that if we consider the algebra of diagonal bounded operator, we have that the restriction of this the infinitesimal generator L to D is in correspondence with the generator of a classical minimal sub-Markov process. In particular, if we assume a trivial assumption that is that gamma is conservative, then T becomes a Markov, quantum Markov semigroup, and the process associated to gamma is a time continuous Markov chain, classical. Now, we need to understand better how the space of configuration of the classical Markov process are. And so we need to introduce this classification, N1, N2, and 3. In the space N1, we have the indexes Ln such that we cannot have that both L and N are absorbing. In the space N2, we have the indexes such that L and N are absorbing, but the corresponding element of the basis EL and EN are not have not the same eigenvalues KL and KN for the Hamiltonian. And in N3 we have the ugly part of our chain. Now, this classification appears when we want to find what are the form of the invariant states. And in fact, yeah, we have that an invariant state as a diagonal part, and what is not diagonal is related only through the N3 part. But what we want, it is characterized NT, and to characterize NT, we need to understand better how the classical Markov chain behaves. And we need a new classification of the class of configuration. In particular, I don't want to be formal, but only to give some ideas. For example, in this case, this is a classical way to, not classical. We want to build a new class of configuration such that two classes are put together if there is a way to connect each other, in particular without considering the direction. For example, in this case, we have that T1 and C1 are connected by this arrow. T1 and C2 are connected by this arrow, and so they belong to the same new class. For the same for the class C3 and T2, while the states I and J are isolated because they are not only absorbing, but there isn't a way to reach them. Now, there is the magic, because when we want to describe NT, we have that NT is the weak star, the closure, or weak star closure of the linear space generated by the projection Pn, more this one, where is the projection on the new class Cn. So it became quite easy to find NT what we want. NT trivial or not trivial, NT composed with a different component or not. Moreover, NT is contained in a set of the fixed point, and we have said that in this case NT is equal to M1, and this family of projection is a family of orthogonal projection, and this is useful in the proof. So now we want to understand what is the evolution of the semigroup to be able to describe M2. And when we try to write what is the limit of this object, we find this, the sum of gam mm plus gam kk and kk minus km, that are the same condition that appears in the composition N1 and 2 and 3. And the second result that links the behavior of the semigroup, the quantum Markov semigroup, with the behavior of the classical Markov chain. So if, for example, if this quantity is different from 0, that it is quite trivial to think that we can control in an easy way this limit. And in fact, we have that when we have not isolated states, we have this result. In particular, if we consider the set of positive recurrent configuration R plus, we can say that it is an attractor for the classical Markov chain. If when we start from an arbitrary configuration K, we enter in R plus with probability 1. And this theorem said that we have that the quantum Markov semigroup is ergodic if and only if R plus is an attractor. So to have ergodicity, we need that we have not class of transient states isolated, for example. And the property of ergodicity gives other implication, because we have that for ergodic quantum Markov semigroup, the coherence is equivalent to the fact that the set of fixed point is an algebra. So we have another algebraic condition to obtain the coherence. And in terms of the classical Markov chain, we have this result. I split the result in two parts, because before we have obtained the result when the set of isolated point is empty, and this is a result published, while here we have obtained a result in the general case, but it is appropriate. And we have that to have the coherence is equivalent to the fact that every absorbing state of the classical Markov chain is isolated, or the classical Markov approach has not isolated states. The set of the recurrent class R plus is an attractor, and every transient states enter in a unique recurrent class with probability 1. So, for example, to come back to my picture, we have that in this case we have not the coherence, because we have two arrows here, but if I cancel one of these arrows, we obtain a semigroup for which the decoherence holds. And so we obtain also similar condition, algebraic condition, not similar, but algebraic condition to study the MD, the coherence that expressed in this theorem. And so by this, we can find example in which we have MD, not ID, or when we have both of them, and so on. For example, in these two cases. And that's all.
Okay, questions, comments, remarks?
In your example of the Laplacian and projection, where the intersection is not trivial, do you have any information about the positivity properties of the projection?
It is a this is a normal condition expectation here. So if we can write directly the conditional expectation, and it is a normal conditional expectation. It's positive. This is so when we write x, x in general is written as the sum of this part and this part. So we define E of x as this quantity. And this is a normal conditional expectation.
More questions?
But for example, you look at for a factor of type 2, is a finite product of
yes,
2 by 2 matrix. Have you quite look what up?
Okay, yes. For until now, we work in general with one normal algebra, but yes.
Since we have examples.
Yes, yes, yes. Because one of the difficulty is to find example in which we can test our conjecture.
Any questions? Comments?
And concerning the generic semigroup, can you express the list of ergodicity properties that you listed as a function of the physically measurable parameters, which are the transport coefficient, the real, the gamma, imaginary,
yes.
imaginary. Everything should be expressed in a final result. Everything should be expressed in terms of this, because this is what you measure.
Yes. Okay. Yes, we have.
I saw in the last slide.
Yes. Not in this last, but here, I think. Yes, because we can express the ergodicity of the semigroup in terms of the attractivity of this class, and this class.
Expressed in terms of gamma, I think.
Yes.
All
Yes. All the behavior is expressed in terms of gamma. Yes. Yes.
More questions? No more questions. Okay. Let's thank the speaker again. And let me